this presentation we'll talk about generalized rotations and more generally how to combine linear and affine transformations in an intuitive way to make other types of motion. We'll come back to this topic several times, so this is just the first time we're going to cover it here. So far we've discussed linear transformations, and this included rotations r theta. It included scalings s alpha beta, and also reflections. What I want to talk about right now is generalized rotation. So r theta, if you recall, was rotation around the origin. So a generalized rotation, we can rotate around an arbitrary point. So a generalized rotation and I'll use the notation r superscript u sub theta. So here, u is a point in the reals, we're still working on R2, and theta is a scalar, an angle. And it means holding the point u fixed, rotate objects around u. So the picture is something like the following. So we're r theta, ru theta is going to holding u fixed, rotate around u through angle theta in the counterclockwise direction. So counterclockwise through angle theta. So the picture for this is just basically, let's just as a standard F position again. Here's F, sitting as usual with its center at the origin. Might as well draw some axes here. So here's the x-axis. Here's the y-axis. And if we have a point U here, and we want to rotate angle theta around U, what's going to happen is we're holding U fixed. So let's suppose we want to go angle theta. And it's in the counterclockwise direction, so it's this a ways. So I think of taking the F and sweeping it down like this. And when we sweep that F around, I think the F comes like this, and it ends up in this picture something like this. So here's the image of the F under ru theta okay. So we'd like to re-express this in terms of rotations and translations. So our goal here re-express ru theta in terms of rotations and translations. So you might want to pause the video here for a moment and think about how would you re-express r theta u, ru theta, in terms of rotations and translations. And when I say in terms of rotations, I mean rotations r theta around the origin, and translations are just translations. So I want to ask you, how do you re-express a generalized rotation in terms of rotations and translations? So you can pause here, think about it for a minute, and then we'll discuss this. So the idea is the following. We have rotations around the origin, r theta, which is the same as r0 theta, and we want to now correct this one here, should have had a u on it. And we want to get a rotation around the point U. So the idea is we want to move the U to the origin, do the rotation, and then move it back. So the idea is first move u to 0, and this is going to be using t minus u. Because remember, translation, this is translation by u, by minus u. Because translation by minus u will shift u to the origin. And then 2 is going to be rotate around the origin, and that's r theta. So this is counterclockwise rotation, holding the origin fixed. And then we move 0 back to u, and that's going to be done by translating by amount u. Okay, and so let's write this out. How do we write this out? We write it as a composition. R u theta is defined to be the following. Well, we're going to take t minus u, r theta, tu, and what order are we to take them in? It's going to be tu composed with r theta composed with t minus u. So it looks almost backwards. We want to think of first moving u to 0, that's t minus u. We then rotate, we then move 0 back to u, that's tu. So we write these in the opposite order of the way we think of them applying to the point. So, in particular, the reason for this is that if you take r theta u of x, that's going to be t sub u of r sub theta of t sub minus u of x. Or if we expand out the translations, that's going to be x plus minus u rotated plus u. Okay, so let's draw the picture here. Here's the axes, x-axis, y-axis. Here's the F in standard position. Here's the origin, of course. Here's our point U. So what happens when we translate F by minus U? I'm going to draw this in a blue color in hopes you can see the difference. If I translate F by minus U, all right, so this is T minus U, is going to send the F to be here. And here's the point minus U, which used to be the origin. So the translate by minus U has shifted the F down. Now we're going to rotate it. I'll use yet another color in the hopes you can see the difference. This will be red. So rotate around the R theta is rotating through angle theta. Right? So that takes the F and rotates it to approximately here. So this point, which was minus U, is now minus U rotated around the origin. And finally, you probably will not be able to see this color. Here's brown. We translate again. So let me write this here. This was the rotation, R theta. Now with this brown color, we're going to translate it to in the direction U. The direction U is here, so the F ends up about here. So the overall effect of the operation was to take the, so this was the translate by U. The overall effect of the operation was to take the F and move it to this F. So our overall effect was this one here. So this is the F as transformed by R U theta. And you can see that in fact assuming I've drawn it well enough on the board, that we have in fact obtained that f could have been obtained by holding u fixed and rotating counterclockwise through angle theta. So implicit in what we just did with generalized rotations is that, in fact, we have that translations and rotations do not commute unless they're trivial ones, in the sense that it matters which order we do rotations and translations in. So in particular, in general, we have that Tu composed with r theta is not equal to r theta composed with Tu. So let's try, so just as an example of this, let's try applying a generic Tu composed with r theta to the f shape, and then the same thing, an r theta composed with Tu to the f shape. So let's start off with Tu composed with r theta. And so here's our standard f shape. So I should draw some axes. Okay, and so our standard f shape sits here. So what happens when we rotate it? When we rotate the standard f shape, it ends up like this. So here's the r theta of the f shape. All right, r theta of f, right? So the blue thing is the f has been rotated through angle theta. Now we want to translate by u. I didn't draw u on the board yet, but let's suppose u is sitting here. Well, when we translate by u, we add u onto every point, and so basically that f shape is still in the same shape, but it's same orientation, same size, but it's repositioned so that what was at the origin is now at the position of u. So this is T sub u composed of r theta of the f shape. So the f has been rotated and then translated. It's written as translation composed with rotation. And that's a fairly intuitive thing to do. You rotate and translate. Less intuitive is the other one. We could translate and then rotate. So let's work on r theta composed with Tu. And again, we want to do it of the f shape here. So this is actually similar to the previous picture we did. So let's draw the axes, x-axis, and the y-axis. Here's the f shape in standard position, starting at the origin. So we first translate by Tu. We form Tu of f. So that takes the f. Here's u. This takes the f and translates it up to be, instead of the origin, the center of the f instead of origin is at the u. So this is T sub u of the f shape is this thing here. It's taken the f and translated it, moved it to u. Now we rotate with r theta. When we rotate with r theta, we keep the zero, the origin, fixed, and we rotate everything in the plane through angle theta. So what happens here is we've got the, I'll draw a dotted line here. Right? We're going to rotate through angle theta, which I'll put like this. So this takes the f, and it rotates it up like this. R theta does this, and it places the f something like this. So the f has been taken here and been rotated over. Think of taking the f, just slide it over. And so then this f, r theta of tu of the f shape is this f up here. So you can see it's in a completely different position than it is here. So this shows that the operations of translation and rotation do not commute. This will be very important when we're writing programs to move things around, because we frequently move them around with multiple operations, and we need to get them in the right order. So that's all for this presentation. Thank you very much.